Hey Phys kids, Campbell here. In this video, we're going to look at Gauss's law for non-conducting spheres. We'll do the plates and the cylinders in separate videos. So, in our last video, we looked at fields of charged conductors. And remember, charged conductors, the excess charge resides on the surface. And so the electric field inside of the charged conductor is zero because there's no Q enclosed. Right, Gauss's law is a surface integral of E dot dA is equal to Q enclosed over E naught. And since there's no charge enclosed inside a conductor, there's no electric field. And so we had this nice graph like this where we had zero inside and then we had the 1 over R squared relationship for electric field outside. Well, what about a non-conducting sphere? So a non-conducting sphere or an insulating sphere, right, the excess charge is going to be set, and it's going to be, if it's a uniform charge density, it's going to be spread throughout. So it's not going to reside on the surface because it can't physically move. So how do we do that? Well, when we deal with charge densities for volume objects, we're going to deal with a volume charge density, which is the total charge per unit volume. Now, a couple things that we need to know when we deal with spheres is when we do our imaginary surface, it is going to be, of course, a sphere that we're going to put at some distance away from the center of the sphere based off, the requirements of the problem. In this case, we're at an R value that is greater than the radius of the sphere, which we're calling the radius of the sphere A. And so remember, when we do Gauss's law, it's the surface integral of E dot dA is equal to the enclosed charge over E naught. And so when we deal with spheres, the area of a sphere is 4 pi r squared. Now remember that this is our imaginary surface. So our imaginary surface. Our imaginary surface, it is going to be a little r because this is my imaginary surface. Unless, of course, I'm looking at the surface of the sphere, and then I guess I'd draw my imaginary surface on the surface of the sphere. I don't know. But if we are outside, if we think about this here, our surface integral, which as long as we're symmetric, right, our electric field is going to be uniform because we're at a constant distance away, and so that's just going to be E. The area of our imaginary surface is 4 pi r squared. The Q enclosed, now I don't have to deal with rho because the Q enclosed is just the total charge, and I want to answer this in terms of Q. So my Q enclosed is just the total charge divided by E naught. And so my electric field in terms of Q is going to be Q over 4 pi E naught r squared. What does that look like? A point charge, right? The normal electric field KQ over r squared equation, r being the distance from the center. So outside of a non-conducting sphere is like the outside of a conducting sphere, which is like the outside of a point charge. If we weren't answering in terms of Q, if we had to answer in terms of the charge density, then of course we would have our rho, the charge density, times the volume enclosed, which, or the volume that the charge is enclosed by. So in this case, if you remember that, or maybe you don't, that the volume of a sphere is 4/3 pi r squared. So for this scenario, if I had to do it in terms of rho, it would be times 4/3 pi. In this case, we'd call the radius A. Oops, that should be cubed. Sorry about that. A cubed. So then we'd just put this in for Q if that was the case, if that's what we needed. So outside, nothing's different. But what about inside? Inside, we have charge all over here. So if I want to do a charge density here, this is going to be a similar vein to what we did when we were inside the Earth and we were looking at the force of the Earth on us. So if we are inside of the sphere, then we have a couple things, because when we look at our surface integral of E dot dA, is equal to Q enclosed over E naught. The dA, well, that's just, the area of my imaginary surface, which is inside this. So as long as I'm symmetric, I know that's a beautiful, writing like this is just not good for me. It's just a regular E. It's just E. The area, of course, is the area of a sphere, which is 4 pi r squared, little r because it's my imaginary sphere. And then this is where the difference is, Q enclosed. Well, now all the charge isn't enclosed. So we're going to have to use our charge density to get at the charge enclosed. So we know that charge density is the charge per volume, right? So this would be like the total charge, I'm just put a little t here, times the total volume. Now, the Q enclosed is, I'm just going to make this a little Q enclosed, would be over the volume that's enclosed. All right, so it's a proportional relationship as long as the density is constant, which means that the Q enclosed is equal to the density times the volume enclosed. Now, if there are some times where you'll get a non-uniform charge density, in which case they'll give you like rho is equal to kx squared or r squared or I don't know, something like that. And that you'll have to plug that in for density. Or maybe they just give you volume density and you just put this in for Q enclosed. Of course, the volume enclosed, we'll have to put an equation in for. But in this question, it asks us in terms of Q. So that means that I'm going to just substitute that in. So Q enclosed, for the density, it's the total charge Q times the volume enclosed, the total volume, which is going to be 4/3 pi a, the radius cubed, right? On my little picture up here, that's the radius cubed. And that is going to then be multiplied by our volume enclosed, which is going to be 4/3 pi little r cubed. And you'll see that we're going to have some things cancel here. And so when I go to plug this in, this is what I have left. I have Q over A, that is a Q, I swear, that is a Q, over A cubed, because the 4/3 pi is canceled, times R cubed over E naught. And so when we go to rearrange this, notice this is R cubed and this is R squared. So that means this is going to cancel with that. And I'm left with, when I rearrange this, the electric field inside a non-conducting sphere is Q times R over 4 pi E naught A cubed. So what that means is that when I'm inside a sphere, my electric field is going to increase linearly until I get to the radius, which in this case is A, but it would be the radius. And then notice if I put the radius in here, so if I was E at A, then this would be Q, R would be A over 4 pi E naught A cubed, and that would give me Q over 4 pi E naught A squared, the radius. So there I'd be at my maximum for electric field, and then of course we're going to decrease with this 1 over 4 pi E naught Q over R squared phenomena once we get outside. So in a conductor, the electric field here is 0, but in an insulator, the electric field increases in a linear fashion due to this R right there. All right, hopefully you got that. You could read my horrible writing. If you have questions, you just let me know.